Alright, welcome back. Now for our next part of our chapter of turning effect of forces. Today we'll focus on the center of gravity. Okay, so for center of gravity, the definition is defined as the point at which the whole weight of the object appears to act for any orientation of the object. So let's take a look at what we have learned previously in the topic of forces. We would like to draw the force of the weight, the free body diagram. So we will usually draw from the middle. We draw a dot. Then we will draw down the force, which is weight. Now, this is what we did in the past. So now we'll officially like to introduce all of these items and what it actually means. This dot right in the middle, the geometric middle of this object is what we call as the center of gravity. Okay, we usually assume that this is the point where the whole weight appears to act. That is why we draw an arrow down and indicate this as weight for all the previous lessons that we have done so. Okay, so remember, this is how we draw weight on a free body diagram using the center of gravity. So for regular objects, let's say a rectangle, you join from corner to corner, one corner to corner, you draw the dotted line. Where the two dotted lines meet, that is the center of gravity. Okay, same for your triangle, from the peak to the middle, from the peak to the middle, from the apex to the middle. Where the line meets, this is the center of gravity. Same for a cube and for a ring. So the ring is slightly special. There is no materials in the middle. So when there's no material, it doesn't mean that the center of gravity cannot be there. Center of gravity is just a scientific concept that we use to explain what happens. So in this ring, although there's nothing there, but the center of gravity can still be right in the middle because this is just the geometric center. It doesn't have to have a matter there before we can assign it as the center of gravity. Okay, so in this ring, we can draw this as a center, we can draw the weight, and this is also how we indicate weight on the object. Okay, all right. So let's ask the question, why does a uniform meter ruler balance on the only at the 50 centimeter mark? Remember, this ruler is 1 meter. Okay, 1 meter, you balance at the, you take your ruler, you place it there, and then you balance. It only balances at the 50 cm mark. If I balance not at the 50 cm mark, what will happen? It drops. Okay, so let's explore this. The ruler has a mass. When you have a mass, remember from the previous topic, you have a weight. Okay, so imagine this is the ruler. Imagine this is the center of gravity. This is your force, and this is your weight. Okay, now I'll put my finger off center. What will happen to the ruler when your finger is off center? So now your finger is like the pivot. Okay, when it's right at the pivot itself, you will see that your this weight W will cause it to turn clockwise. Correct? So this causes it to have a moment, and this moment of the weight is not zero. This causes the ruler to turn clockwise about the pivot, and as such, it falls. So let's see. We demonstrate off center, it falls down. Okay? Now, what happens if we place our finger right in the middle? If we place our finger right in the middle itself, we will see that the ruler will be balanced. So let me try. You can see that it balances because now our finger is counteracting the force of the weight of the ruler. So in this case, the moment of the weight will be zero. It is balanced, or what we call as equilibrium from the previous topic, previous chapter, the previous section. Okay. So that is for center of gravity, a very short part itself. We'll come back for stability next. Okay, thank you.